right, so the question here was, what distance will the human move under the following circumstance? So the human's on ice with a coefficient of friction of 0.02. And so they're there and they throw this rock, this 3 kilogram rock at 8 meters per second to the left or the negative direction, according to the coordinate plane that I drew, which just a little tidbit here, it is very important to label your axes and also label where the 0 is. So when you're giving your answer, we know where the 0 was. But anyways, humans throwing the rock that way. And so what's going to happen is they're going to go back the other way. Since this is something called a Newton's third law of pair, where you probably heard every action renders an equal and opposite reaction. So that equal and opposite reaction is the human moving to the right when the the rock is moving left. So how I would approach kind of going into this problem is I think about what they're asking for. So they're asking for a distance. So my brain automatically goes to these kinematic equations where the x is kind of already in that equation. And so they don't give us time. So I'm going to try my best not to screw with that. So I automatically gravitate to this bottom equation here. We do need two things though. We need this initial velocity, so the recoil velocity of the human going back, and we also need the acceleration. That acceleration is going to be acceleration due to friction there. Basically, how much the friction of the ice is slowing the human down. But yeah, and then this final velocity is going to be 0 because we want to know the distance when she finally stops. So let's just go down the list and find these variables. So for the initial velocity, when we're given masses and velocities, my brain goes straight to momentum, just because we know that momentum equals mass times velocity in this equation here. This is the law of conservation of momentum. M1v1 plus M2v2 equals M1v1 plus M2v2. Left-hand side is initial conditions, and then right-hand side is final conditions. And by final, I mean like right after the rock is thrown, not anytime after, like instantaneously there. And so if we're plugging in the numbers, let's say object 1 is the rock and object 2 is the human. We plug in the numbers. They both have initial velocity of 0. So the left-hand side is going to total 0. And so that means that the right-hand side, the final conditions, the net momentum also has to equal 0. So we solve for that equation and we get that the final velocity is 0.343 rounded. And side note, when you're doing your calculations, I would not round them. I'm just rounding them for the sake of not running out of space on the page here. But anyways, next we have to find the acceleration. And when we're thinking about acceleration, my brain goes to forces because forces cause acceleration. So we all know F net equals mass times acceleration. And so if you see in this diagram here, the net force is friction. The reason why this gravity and normal force are equal to each other, as seen by these little tick marks here, is because if they weren't equal, then like let's say the normal force was much higher than the gravitational force, then the human would probably fly up. But if the gravitational force was bigger, then the human would fall through the ground, so on and so forth. So yeah, the net force is going to be that frictional force. And so we know friction equals coefficient of friction times normal force, and normal force is going to equal gravitational force, which equals the mass times the acceleration due to gravity. So doing some substitutions there, force equals coefficient of friction times the force of gravity, since it's equal to normal force. So then we do some more substitutions, masses cancel, A equals mu times gravitational acceleration, and then we get that for the acceleration, and then the rest of the problem is just plug and chug into this bottom kinematic equation. But yeah, and a little thing to note is that this is in the positive x direction. I probably should have said that, but thank you for watching. Let me know if you have any questions.